This presentation is about a new result on robust adaptive dynamic programming for uncertain partially linear systems. This is a joint work between me, Farnaz, and Professor Svante Gunnarsson at LIU. Over the past 2 decades, dynamic programming has been used to develop reinforcement learning algorithms for model-free control of dynamical systems. On-policy and off-policy routines are 2 well-known examples. These algorithms have been shown to produce stable policies when the dynamics is purely linear. But the point is that in practice, we do not have a purely linear system. In this presentation, we consider uncertain partially linear systems. We have a linear subsystem like this, where we can measure the state variable x, and for this system, we aim to optimize a quadratic cost function, which we represented in 3. We do not know A, so we aim to use the on-policy or the off-policy routine to control such a system. This linear system is, however, subject to some uncertainty, which is represented by delta. Delta is generated by a nonlinear system where the dimension and the dynamics are not known to us. The only thing that we know regarding the nonlinear part is that we know an upper bound for the L2 gain, and also we assume that the output delta is available for the measurement during the learning procedure. So the point and the question is like this: can we still apply the same on-policy and off-policy routines on this nonlinear, uncertain, partially linear system safely without endangering the stability of the total system? In the theorem, we give a simple sufficient condition, which is actually a design criterion for the quadratic weighting matrices Q and R, such that the stability of the total system during the learning procedure is guaranteed. This is a simple design criterion, and we can satisfy it easily. For the simulation result, we consider 2 inverted pendulum, which are connected by a spring. We consider pendulum 1 as the linear system that we want to control, and we consider pendulum 2 as the nonlinear uncertainty. So we fix the controller for pendulum 2, and then we aim to learn the controller for pendulum 1. We apply the off-policy routine on this example. And after running the off-policy routine, we have 2 observations. The first observation is that the system remains stable during the learning procedure. And the second observation is that the controller for pendulum 1 converges to the optimal controller, to the analytical control and the optimal controller. And with that one, I conclude my presentation.